AP Chemistry. This is part 3 of the Thanksgiving midterm assignment answers video. And now we move on to some more advanced problems. You saw this problem on the day 18-19 assignment, and I told you back then it's a problem I'd really like you to learn, memorize it, because there's a couple of things going on here, several things going on here that are kind of advanced and can be tricky in solving a problem like this. And so I want you to be able to recognize what those things are. So let's go ahead and read it. So seawater has a density of 1.057 grams per milliliter and is comprised mainly of sodium chloride and water. What is the molarity, so we're trying to find molarity, of a solution that is 2.56 mass percent sodium chloride? Okay, let's start off by identifying what we're looking for. We're looking for molarity, and that's moles of solute, and in this case the solute is NaCl. And that's over 1 liter of solution. The solution is the NaCl and the water mixed together. Okay, so that's our target. That's what we're trying to hit with this problem. All right. And then it says the seawater is a density. It gives you a density comprised mainly of sodium chloride and water. What is the molarity of this? Okay, let's start up here though with the density. How do you deal with that? You can see that it's a top-bottom kind of a number. And so the way you should write this is this way. Now, grams of what? Seawater has a density. So they're talking about the solution, the seawater solution. That's the salt and the water together. Over grams per, and remember, you don't see a number next to milliliter, but it means it's 1 milliliter. For every 1 milliliter, you have 1.057 grams. So what we're doing is turning this into the 2 conversion factors that we'll need somewhere in this problem. So that means you can also say the following, that for this particular problem, okay, 1 milliliter of solution over 1.057 grams. So you can just flip it. You don't have to write out the equivalency, 1.057 gram solution equals 1 milliliter solution. Just go ahead and go straight to the conversion. So they give you one of the conversion factors. You just have to recognize that there's a 1 in front of that milliliter. And so we wrote it like that, and then we flipped it. Okay, so that takes care of that. That's going to be a conversion that we're going to use in this problem. Okay, and it's comprised mainly of sodium chloride and water. What is the molarity? We took care of that over here. Of a solution that is 2.56 mass percent of sodium chloride. So remember what 2.65 mass percent means. It means that if you have 2.56 grams of NaCl, in order for that to be a 2.56%, it would have to be over 100 grams of solution. Okay? There's an infinite number of combinations that I could put here to get 2.56 mass percent. But just confirm that. Divide 2.56 by 100 grams and multiply by 100, and that gives you 2.56 mass percent. That was the formula for mass percent. If I took double 2.56, it gives me 5.12. So 5.12 over 200 grams of solution would also give me 2.56 mass percent. There's an infinite number of possibilities. So when they give you a mass percent, what do you do with it? Well, you convert it into some very specific number of grams. You get to choose how many grams you're working with. So this is the key to this problem. So you always choose 100% because it's a nice round number, and it just simply turns that percent into the number of grams. All right, so what we're going to do is we're going to say that we're starting with 2.56 grams of NaCl. Okay, and that's in 100 grams of solution. That's what 2.56 mass percent means. So we get to choose how many grams we're going to work with. Okay, so now we're ready to start our problem. This is our starting point. This is our ending point. Okay, so we have to get from grams of NaCl to moles of NaCl. That requires a molar mass conversion. And that conversion is, there's 1 mole. Okay, that we computed that earlier in an earlier problem. Okay, so we're going to start with our first box. So we're going to start with the top. Okay, we always pick one or the other, top or bottom. I always start with the top. So which of these two is going to go in our first box? Think about that. Okay, we need grams to cancel out and moles to appear on the top. So we need grams on the bottom here. So we're going to choose this one. Okay, grams of NaCl cancels and cancels. So now we have moles of NaCl on the top. That's what we want. So we're done with the top. Now we have to get grams of solution to liters. Now these are two totally different units of measure. Grams measures mass and liters measures volume, how much space it takes up, like a 1 liter bottle of water. Okay, and this is how heavy it is. Well, for water it's easy. It's a 1-to-1 relationship. There's 1 gram for every, actually 1 milliliter. But here we have two different, again, this is mass, this is volume. Fortunately, we have a conversion that we were given in the problem. It's this up here. That's what density is. It relates grams, mass, to volume. In this case, milliliters. All right? So the first thing we want to do is go ahead and convert to milliliters and then eventually to liters. So which one of these two conversions up here are you going to put in that box so that grams cancels and milliliters appears on the bottom? Okay, well, it's going to be this one. And it's of solution. The seawater is the solution. That's the mixture of the salt and the water. So it says the seawater has a density. So that means the solution has that density. Okay, so now grams of solution and grams of solution cancel. So now we have milliliters of solution. We need to get the liters. And of course, it's this same conversion we've been using. Now, this liters to milliliters applies to any substance. This 1 liter equals 1,000 milliliters is any substance, but we're interested in the solution. So that's the way we're going to write it. We need liters to appear on the bottom and milliliters to cancel out. So we're going to put the milliliters up on the top. It says solution, crowding it in there, and 1 liter solution there on the bottom. So milliliters of solution cancel. So we have moles of NaCl on the top, liters of solution here on the bottom. Everything is set up properly. Okay, so now we multiply everything on the top, 2.56 times 1 times 1.057 times 1,000, divide by everything on the bottom, divided by 100, divided by 58.44, divided by 1, and that gives us 0.46 moles per liter. Significant figures if you want to do that. 3, 3, 4, 4, 4. Well, assume 4. So we can go to 0.463. Okay, and really the way you should write that final answer is capital M, molar. Okay, so that's the answer to that. So I would put a star by this problem. I'd really learn this. Again, the two tricks are, what do you do with that density? You turn it into two conversion factors. And what do you do with mass percent? And you do this almost every time you'll have a mass percent in a problem. You take that 2.5 mass percent and you get to choose what sample size you want to use. So you're going to choose 100 grams. So if it's 2.56 of 100 grams, then it's 2.56 grams. And that's how we wrote it over here. 2.56 grams of NaCl over 100 grams of solution. You can't work with a percentage in these problems. You have to get it to some tangible number of grams, and that's what you did here. So those are really the two tricks to this problem, and those And those are things that you need to be aware of. Okay, so you're going to go ahead and do 1B. All right, and now we're on to 11A. What is the molality of lead ions in a solution that is 400 parts per million lead ions? Okay, so molality. So what is that? I'm going to come over here. It's moles of your solute, which is lead, Pb, over kilograms of your solvent, and that's going to be H2O, not the solution. All right, so what is a molality of lead ions that's 400 parts per million? Okay, what parts in this case means, you have to understand this is parts means grams per million grams. So that's what parts means. It's not moles, it's grams, all right? So we're going to start off with 400. Grams, and it's grams of Pb over, and it's grams of the total solution. So I'm going to actually do something I don't usually do. It's per 1 million grams, I should say. I'm going to actually break this into, instead of saying solution, I'm going to say Pb plus H2O. You could have said solution, but there's a reason why I'm breaking this out like this, is because you're going to need to do the same thing here in just a second. Okay, so it's, again, I'm simply chose to write solution as the solute plus the solvent, and that's what it is right there. The reason is at the end we need to separate out the solvent for our final answer. So that's why we're going to do that this time. All right, so we have 400 grams of lead and 1,000,000 grams of lead plus H2O. So we eventually need to get it into just kilograms of H2O. So we're going to have to separate these two. So the first thing you do in this problem is you come down here and you do a subtraction problem. It's a little unusual in these problems to see subtractions and additions, but they happen sometimes. So it's 1,000,000 grams, I should have written, 1,000,000 grams of lead plus water minus 400 grams of lead. Okay, that's what we know up here, equals 900, get your calculator out for this one, 999,600 grams, get that out of here, it's confusing, of H2O. Okay, so now we know how many grams of water we have, we know how many grams of lead we have, we know how many grams of the solution that we have. All right, so what we have here, and I didn't write grams there. So a couple things. Grams to kilograms is a simple conversion. There's 1 to 1,000 relationship there. But what we have to do is convert somehow from Pb plus H2O to just H2O. So how do we do that? Well, from this we know that we have the following relationship. That for every 1,000,000 grams. So what this is saying is for every 1,000,000 grams of the solution, Pb plus H2O, we have 996,400 grams of H2O. So now we can turn that into two conversion factors right there. This one over this one, or this one over this one. So what we want to do first is get rid of PbH2O down here and come up with just H2O. So you're going to choose one of those. Which one over which one? Does this go over this or this go over this? Think about it. Well, we want to end up with just H2O down on the bottom here. So we're going to do it this way. I'm going to write maybe a little small because I don't want to run out of space here. Okay, so we have 1,000,000. That's 6 zeros. Grams of Pb plus H2O. Okay, so I have grams of Pb plus H2O down here. Cancels with grams of Pb plus H2O up here. So what I've managed to do is get grams down here in the denominator. Okay, now and you can see what I'm doing now is I'm working on the bottom first. I kind of skip the top. Okay, we'll do the top second. Again, it doesn't matter which order you do it in. Okay, so now we need to convert from grams to kilograms. So we know from our conversion that there's 1,000 grams that equals 1 kilogram. So we need grams to cancel out and kilograms to appear. So we're going to do this. Okay, so grams of H2O cancels with grams of H2O, and we have kilograms H2O on the bottom. So we're looking good there. Now, one more conversion to do. We need to get from grams of PB to moles of PB. I'm going to erase this because I need the space. And I'll just write the answer up above here. But we need to get from grams of PB to moles of PB. That's a molar mass conversion. So 1 mole equals, and you just go to your periodic table, and there's PB lead. It's 207.2. I'll hold it up a little closer. 207.2 grams. Okay, so one of these goes on the top, one of them goes on the bottom right here, which is which. Again, now we're dealing with the top. We're done with the bottom. We got kilograms of H2O, kilograms of H2O. Okay, so which goes on the top? We need grams of PB to cancel and moles of PB to appear on the top. So that's what we're going to do here. Okay, so grams of PB, and you got to go all the way over here to cancel grams of PB. It's not right next to it this time, and that'll happen in these problems. So now we have moles of PB on the top. That's for our final answer. We have kilograms H2O on the bottom. That's for our final answer. We have the units set up. So I'll go ahead and write the answer up here. So we've got 400 times 1 million. Now if you want to simplify it now, you could go ahead and cancel the million there and the million there. But I've never done that before, so I'll leave it as a million. Times 1,000 divided by 1 million. Divided by 999,600. Divided by 207.2, and that gives us 0.00019, and it's small m for molar, moles per kilograms of solvent, and that's molality. So that's our final answer. Okay, and I just checked my work as you should always do, and I missed by the decimal place by 1 position. So let me go ahead and erase this. The second time around I got 0.00, 2 zeros after the decimal, 19. Okay, so this is another problem typical of what somebody who works at the water department would want is 400 parts per million of lead in the drinking water. It's probably too high, but that's something they want to know. It's very small concentrations. Okay, so you go on and do 11B. Okay, 12A, we move on. So what is the mole fraction? We're trying to find a mole fraction here of sucrose, and that's C6H12O6, so I just usually abbreviate that. Okay, so we're going to move on to problem 12A, and it's what is the mole fraction of sucrose? So I've already written the formula there. Let me write that plus sign a little bit better. What for mole fraction for this particular problem? So it's moles of solute over total moles of solute and solvent. So that's moles of sucrose, moles of H2O. I generally abbreviate sucrose. It's got a formula C6H12O6. That's too long for me to write, so I just abbreviated SUC for sucrose. So everything is on the bottom and the sucrose is at the top. A mole fraction is dimensionless because all the units moles cancel out, so it's just a number. So now what you're going to start with is 4.33 molal of sucrose. So let's come over here. So over here, what we're going to have for our answer is just simply a number, a fraction, some kind of or a decimal. It's called mole fraction, but it's always expressed as a decimal because we work with calculators that work with decimals. All right, so we're going to come over here, And let's draw a line here. That's just our general formula, 4.33. Okay. And what we want to end up with moles of sucrose on the top. So we already have moles of sucrose on the top. Okay. In fact, I'm going to write that over here. It is dimensionless, but let's write the units that we're shooting for, because that's what the purpose of doing that is. So it's equals, and I'm just taking this and writing it over here. Okay, there you go. All right, so now that's what you're shooting for. That's your mole fraction. So you have moles sucrose on the top already. What we need to get on the bottom is moles of sucrose and moles of water. So we already know moles of sucrose. So we're going to go ahead and let's go ahead and just fill these numbers in. We have 4.33 moles. Moles of sucrose is in the denominator as well. Plus, we need moles of water. We don't have moles of water, we have kilograms of water, because that's what molal is expressed in, is kilograms of water. So we have to do a conversion down here. So let's start with 1 kilogram. And molar masses are expressed in grams, not kilograms, so we want to get to grams of water. So kilograms cancels and cancels there. All right, and then we have a molar mass, because we need to get to moles from grams. So we know that one, most of us off the top of our head. Grams of H2O cancels and cancels. So it's 1 times 1,000 times 1 divided by 1 divided by 18.02. So that really just comes down to be 1,000 divided by 18.02. And that gives us 55.5 moles of water. So now we can stick that here for moles of water in the mole fraction formula. Okay, so now we just solve that problem. So it's going to be 4.33 divided by parenthesis 4.33, because I have to add 2 numbers, and I want that to happen before I do the division. And that's 55.5. Close the parenthesis, and that gives you your mole fraction of 0.72, if you want to call it that. And again, it's a decimal number, even though they call it mole fraction, but there are no units to it. So that's the fraction of that solution that is made up of the sucrose. Okay, you go ahead and do the next one, 12b. Okay, so again, this problem is a little bit different. You have to do it in pieces. You're given this, so that's going to go. That number is going to go there and down there, and then you have to figure out how many moles is in a kilogram of water. So moles of H2O, and once you figure that out, that's going to go there. So that gives you your final answer. All right, you do 12b, and I'm going to move on to 13a. Okay, if 1.5 liters of a 5 molar solution of sodium hydroxide is diluted to 6 liters, what is the molarity of the new solution? Okay, so this is called a dilution problem. It has the word diluted in it. That means you made your lemonade too strong, it's too sweet, it's too syrupy. So you want to add water to make it less sweet, less syrupy. That's what you're doing here. It's a very simple formula. It's probably, I mentioned there was one time when you don't change molarity, capital M, into moles per liter. You just leave it as molarity, and it's in this formula right here. And it's just simply a ratio. If you have a certain concentration, molarity is moles per liter, volume's liters. You multiply those two, you get moles. So you have a certain number of moles. What you want to do is reduce the concentration of the number of moles, and you do that by adding water. Okay, just like you do to lemonade that's too strong. So let's go ahead and write this out. It's pretty straightforward. So write out the formula. That's beginning molarity times beginning volume equals final molarity times final volume. That's the way you would interpret that. So the beginning molarity is 5. I'll just write it directly below the numbers here. I'm going to omit the trailing zeros. The volume is 1.5 liters. I should write molar here. Okay. And that equals, it wants to be diluted to 6 liters. And it wants to know what's the molarity, M2. So that's what we're trying to figure out. So it's a very simple algebra problem. So you divide both sides by 6 liters. These cancel. And you have M2 equals 5 times 1.5 divided by 6. And we'll go ahead and do that problem. And that gives us 1.25 molar. So another way, it kind of makes sense here. You started off with 5 molar. You took the number of liters and you basically multiplied it by 4. 1.5 times 4 gets you up to 6. So what you did is you cut the molarity by times 1/4. You cut it times 1/4, so 5 times 1/4. In other words, a reciprocal of 4. 5 times 1/4 would give you 1.25. So you made your lemonade concentration a lot weaker, and that's all there is to that. So again, the key word to look for in those problems is the word diluted or dilution, and that will tell you that it's one of these M1V1, M2V2 type problems. Very simple to solve if you know what you're looking for. Okay, you go ahead and do 13B. So I'm going to move on to 14. All right, a solution is made by dissolving 12.35 grams of glucose. And again, rather than this, I just write glue, GLU, in 25 milliliters of water at 25 degrees. Calculate the molality of the glucose in water. Okay, well, this is a pretty straightforward problem. It comes out of your book on page 544. So we're going to come over here. We want molality, which means we want moles. Okay, so we want that. That's molality. And we start off with this. Okay, so we have to go from grams of glucose to moles of glucose. That's a molar mass conversion. On the bottom, we have to go from milliliters to kilograms. Now, that's a unit of volume, how much space something takes up, and that's a unit of mass. So when we dealt with that in the earlier problem, 10A, we had to have a density to relate volume to mass. But there's already a relationship that exists that you should have memorized, and it's this. It only applies to water. So we're going to write this down below. And it's this. In other words, density was defined around the properties of water, as much of the metric system is. So 1 milliliter of water equals 1 gram. It relates the volume, how much space the water takes up, with the mass that it has. So if you have a milliliter of water, you have exactly 1 gram. If you have a gram of water, you have exactly 1 milliliter. You can multiply those by 1,000 and get 1 liter equals 1 kilogram, or 1,000 grams. And if you look at a bottle of water that you buy at 7-Eleven, for example, that's a 1 liter bottle, you'll see that it has a mass or a weight of 1 kilogram or 1,000 grams. All right, so that's only true of water, is that relationship. If it's anything other than water, you have to be given a density, as I say, like we did back in problem 10A and 10B, where they have to give you the density of the solution or of the substance. Okay, so here we go. So now what we can do is we need to figure out the molar mass of glucose. It's C6H12O6. So let's just do that formally this one time. So C, you have 6 of them. Okay, and if you add those numbers up, you get 76.06 plus 12.12 plus 96, and that gives us, it doesn't seem right. Let me try that again. Okay, if you add those up, that gives you 180.18 grams per mole. So 1 mole of glucose Okay, so one goes over the other. So we're going, which one goes on top? Let's go ahead and draw our box. Okay, which one top, which one bottom? You need glucose, grams of glucose to cancel, moles of glucose to appear on the top. So you're going to put this one on top. Okay, so grams of glucose cancels with grams of glucose. Now we have moles on the top. So we're done with the top. Now the bottom, we have this. And again, I didn't give myself enough space. I should have started way over here. So I'm going to erase this, get it out of the way, but I'll keep the units here. You'd think I'd learn by now. Okay, so we have milliliters. We need to convert to liters. So 1 liter equals 1 kilogram. I wrote it in terms down here, milliliters. 1 milliliter equals 1 gram. So let's write the other conversion. 1 liter H2O, because this is really what we're interested in, is 1 kilogram H2O. So those are both the same thing. Just this is 1,000 times greater than that on both sides. So now we got milliliters. We need to convert to liters. So we've got 1,000 milliliters for every 1 liter, and that's of H2O. I really blew it here. I should have really just did not give myself enough space. So let me get rid of that for now. Okay, milliliters of H2O, liters of H2O. Okay, so milliliters H2O, milliliters H2O cancels. And now we need to get from liters to kilograms, and there's our conversion right there. So it's 1 liter H2O for every 1 kilogram of H2O. Liters H2O cancels. So now I'm going to go ahead and move down here for the answer. And what it is was molality, so it's moles of glucose. That's what we're looking for. Okay, so moles of glucose appears top, and kilograms H2O bottom. So we got everything set up properly. So it's going to be 12.35 times 1 times 1,000 times 1. And then you divide that by 25, divided by 180.18, and that gives you 2.74 moles of glucose per kilogram of H2O. And of course, the other way to write that is 2.74. It's molality, so it's small m. And that's your final answer. Okay? All right, so you go ahead and do 14B. Write everything out here because I want to be sure this is being reinforced. Don't skip any steps. I want you to write this out. I want you to write everything that I did here out. And that's it. Okay. All right, let's keep going. 15A. All right, a solution is made by dissolving 16.25 grams of glucose and in 0.24 kilograms of water. What is the mass percent of the solute? So let's go ahead and write what mass percent is over here. So it's grams of glucose, that's the solute, over grams of solution. But instead of writing solution, I'm going to write grams of solute, because the solution is the solute plus the solvent, plus grams of H2O. Because we're going to need to figure out that, quite possibly. All right. Okay, so that's what you have. So you need to kind of solve for each of these. So we already have grams here. So I'm going to write that over here, way over here. I'm not going to take any chances this time. Grams of glucose. That's going to be on the top. Over, it's kilograms of water. Okay. Okay, that's what we're starting with. And they want to know the mass percent. So to get mass percent, we need to find these three, and we need to then multiply by 100%. Okay, so we're not going to do this again. And when it's got a plus sign there, like in the denominator, like either mole fraction or mass percent, you kind of have to break up the problem. So let's start with grams of glucose. We were given grams of glucose, so we already know that. Then on the bottom, we need grams of glucose again. We know that. And now we need grams of H2O. So this is really just one simple conversion to convert from kilograms to grams of H2O. So let's just do that. And there's 1,000 grams for 1 kilogram. And you multiply that and you get 240 grams. Kilograms canceled there. And that's of H2O. So now we have everything we need. We have grams of H2O, grams of glucose, grams of glucose. So what I'm going to just do is combine those. We're really not writing an equation across here this time. We're just going to go ahead and combine these. So grams of glucose over, again, plus this. Okay, and when we do all that, we'll put that number right here, so it's 16.25. I'm not showing you my calculation this time, but I'm going to divide, open my parenthesis, and then add 16.25 plus 240 on the bottom, close the parenthesis, so that my order of operations is correct, and hit 0.0, that's 0.063. I'll go ahead, two significant figures there. So now to get the percent, we have to bring this down here. Times 100%, and that's going to equal 6.3%. Okay, and that's your final answer. So it's 6.3. The mass percent is 6.3%. Okay. All right. We can go ahead and you can go ahead and do 15. And let's move on to. Okay. Well, I've gone a little past my 30-minute time limit that I like to try to set for these videos. So I'm going to cut this one off. We'll do the rest of the problems on a later video. We'll see you then.